Yeah, so hi, I'm Matt, and he's Dan, and we like to call up, come out here, and we like to call ourselves Team Walrus. Please don't make us answer why. So this is going to be a two-part talk, basically. First off, I'm going to be giving sort of a brief overview of the world of RF access control. And then Dan, supposedly, is going to be talking about attacking that RF access control, and then introducing Project Walrus, which is the actual app that we've developed. So he's going to go away, and I'm going to do part one. So a brief overview of RF access control. So what is physical access control, right? We know that it's restricting physical access to, a specific location or a specific resource. And at this part in doing my slides, I said, kill me now. Because I was doing, the usual thing that programmers do, and doing a death by PowerPoint, enumerate every single thing in an object-oriented fashion, like no one's ever heard of access control before, or locks, or anything like that. So instead, I'm going to treat you as the intelligent people that you are, right? You know what access control is. You know what physical access control is, right? I mean, it's preventing access to, a resource, or a specific location, or a location with interesting resources even. And you know the way that we protect against those resources. We use physical access controls like walls or guards or locks. You may know what those are. We don't use guard cats. We use CCTV cameras, and we know the credentials that we use in these kind of things, right? We started off very simple. We started off with just ID cards, basically. Moved to keys. You might have heard of those. Magstripe, for example, RFID. And currently we're all in the way of, the dystopia future of biometrics, where, your eyes, your hands, your legs, your face, and your smell apparently can all be used to identify you. So access control, right? Prevent access to resources or locations. We have the credentials, that sort of thing. So what this talk is specifically going to be talking about is cloning. Well, no. Part one is talking about the world of RF access control. So RFID, well, not RFID, RF, radio wireless access control. Or rather, it's going to be talking about the confusing giant messes, this world, basically. So I'm just going to be talking about the technology, first off, in general. So what I'm going to do is sort of establish a way that we can sort of classify the specific implementations of RF access control that I'm about to talk about. So there's a whole range of access control things, and normal people like us normally have access to these things, just like in our workplace or in our where we live, that sort of thing. So they're not unusual things to see, but there's lots of them. So I've sort of classified them into sort of four sort of different, I'm sort of going to talk about them in four different ways. So we're going to talk about them first on like a physical, the actual physical, the radio frequency layer. And then there's like a data layer, so how these cards actually, what do they actually have on them? What makes them, what is the actual credential that these cards hold that is used as the identification factor? The protocols, so how do the cards actually pass this information to the readers that they're being used with? And then the system architecture as a whole. So I'm going to start with system architecture because this is actually sort of almost the same for all of the systems that I'm about to talk about, all the different kinds of cards. So we'll just talk about this first in a sort of generic sense. So at the bottom of your sort of tree system architecture for things, you have your actual input-output devices. So you have your locks, your actual readers, for example, and they'll be connected to site-specific controllers. So for example, at a polytechnic like this, each sort of block might have a controller which is controlling all the locks and all of the readers and that thing, and all of those will be talking to one sort of master controller. And this master controller is the one that actually will have, the actual database of everyone's user credentials, that sort of thing. And then usually you have some kind of administrative terminal which is connected to that, which actually does, people would actually manage the cards from. And there's a variety of protocols in here in use, some of which you may know, some of which you'll find out, and some of which you probably don't know. So WGAD, Serial, Clock and Data, OSPD, and then there's terrible proprietary things which are just, no. And then, as you go up, you start to get a little bit more modern. So I think, now sort of like IP is usually a thing, controller is a controller. OSDP stands for Open Security Device Protocol. I forget, it's kind of a new sort of thing that's sort of come out, and they're trying to standardize communications in these sort of networks with that. And then on the actual controllers of the admin PC, you just have good old-fashioned IP or good old-fashioned proprietary crap. Now, these networks can be more complicated than that, obviously. You know, they can have, you can integrate your CCD cameras into these controllers, for example. You can have displays, room displays on each sort of controller to say who's in what room, and, like a meeting display kind of thing. And of course, you can connect it to your elevators, your lifts, whatever, using like a sort of terrible extension interface to your controller. And of course, this is a great way for them powers that be, the access control people, to make lots of money. But this is good from our perspective because it actually introduces all of these sort of, as we'd like to say in pen testing, and it expands the attack surface area, right, of all of this system as a whole. So generally, the locks and the I/O devices and the readers and the cameras, they're all treated like in an unsecured area, and the rest of it's treated as being secured, right? So hopefully you'd hope that this is what's actually happening in the real world. So, people aren't just leaving their controllers, accessible to people, as you walk in, right? So the answer is no, and as you'll probably see in talk tomorrow by our colleagues, there's been instances where we've found people who just leave these controllers like unlocked in the basement. So they have amazing, RF access control system, but you just walk into the garage, unscrew a door or something like that. You don't even have to lockpick. We just unscrew the door from its hinges because we're not good lockpickers, unfortunately. And then you once you gain access to the controller, you have access to all everything you need here. So there's a lot of attacks that can be done on the world of RF access control and just access like security systems in general. But we're only going to be talking about the actual cards and card readers sort of part, the actual RF part. So now let's talk about some actual implementations of RF access control, or rather the ones that I know or actually care about. Because I'm not here to talk about your rolling car key fob, and I'm not here to talk about the terrible thing that you got from, well, we'd call it the warehouse. I don't know what you guys would call it, but a terrible 4-channel RF sort of garage door opener thing. We're going to talk specifically about access control and about cards, basically. So let's do that. So let's start from sort of the simplest sort of side of things. So we start off with HID procs and EM. So HID is a giant corporation which sort of has a very large interest in sort of these access control systems. HID procs is one of their brands. EM is actually, so EM4100 is a chip. It's like, just like it's a chip that you can buy the license for, and then you can use it in your own embedded devices. So there is actually no EM brand per se or anything like that, and you might not know that you actually have one. It's not quite so obvious as a HID proc sign, which will have their logo stamped directly on the card. But EM is also sort of well used as well. And I've decided to sort of, I'm going to talk about them at the same time here because they're pretty much similar. You'll see. I say they're similar, and then the very next slide I'm going to show how they're different. So you just have to bear with me here for a bit, but just trust me. So first, let's talk about the physical and RF layer of these sort of cards. So when I say physical RF, I mean you've got some data on that card that needs to be sent to the reader. So there's different ways of actually encoding that, and then there's different ways of actually modulating that onto a certain frequency. Now, I'm not here to talk, I'm not going to bore you with the wonderful world of actually modulation and encoding and that sort of thing. I'm just going to point out like the characteristics of each of these systems in the RF sense, just for the people who are actually interested and actually kind of already know how these things work. So, how I said these systems are similar, well, they're different here, but then they get similar, so bear with me. So, for example, EM and HID procs, they'll both run at 125 kilohertz nominal. And there's two sort of main frequencies that these cards you'll see will be working on. There'll be 125 kilohertz, we call that low frequency, and then 13.56, which is the higher frequency one. That standardization is purely because the chips and the actual antennas, that sort of thing, it's easier if we standardize on those and then let all the companies that want to do the application level and stuff like that, then they can all fight over the proprietary bullshit over the top of that. Oops. But and the RF layer, they've sort of standardized because practical reality is actually building these chips and antennas and stuff like that sort of come to play. And so EM uses amplitude shift keying, well, on-off keying, and HID-prox uses frequency shift keying, and they use Manchester biphase PSK. So you'll see, I won't bore you with what these terms actually mean, but they're just different ways of actually converting the data on the card to an actual physical waveform. So one interesting thing about these cards that will talk about in the RF level is how they actually get powered, right? I mean, these cards there's two different ways of powering having these cards powered. So there's active and there's passive. So an active sort of access card is one that has a battery in it, right? So you'll see these in like UHF tags that you'll put on your car to sort of like get into it. They have a very long range reader. When I say very, I mean like 20 meters to get into a car park or similar. But the cards that we're talking about here, the HID cards, EM cards, that sort of thing, they're passive, right? So they don't have a battery built in. And if you look at the actual design of the cards, they're very simple. It's just an antenna around the outside of the card, wired into a chip. That's pretty much it, and then covered in plastic, obviously. So how do they actually get their power? So you're going to see this term, aka this guy's last name, quite a lot. And this is the only picture that you're actually going to see in this entire talk. This guy is important to the world of wireless sort of access control in general. And his name, to use a programming term, his last name has been overloaded very heavily into a whole range of different terms. So this guy invented the produced the WeGAN interface. So that's a way that a reader can interface with a controller and a reader can interface with each other. So that's just simply, two lines, data 1, data 0, nothing special there. But he also figured out the way to power these sort of wireless cards. That's using something called the WeGAN effect. So you have your card, it's currently just an antenna and a chip. You bring it towards a reader, and what that reader is doing is it's constantly emitting a EMF field, EM field, I guess, it's like pin number, isn't it? EM field. And what happens is, so it's an AC alternating field, and basically the card can inductively, with its own antenna, inductively pick up that field, rectify it back into DC and smooth it and everything, and then it can use the sort of power transmitted from the reader wirelessly through that field to power itself up. So the reader's giving energy to the card, and in return the card's giving data back, and this is the WeGAN effect. So both HID-prox and EM and all of the following cards that I'm about to talk about all use the WeGAN effect. Okay, so let's move on to the data layer. So in this section I sort of want to talk about what's actually on these cards that is the identifying factor. So in the case of HID-prox and EM, they just store a static bit stream of data. So the interpretation of this bit stream is completely dependent on the configuration of the system. And so this guy shows up again. So we have the WeGAN format. So our card, for example, one of my HID cards might have, it'll have a 26-bit number on it, zeros and ones, binary number. And so a certain portion of it will be dedicated to the card number, a certain portion will be the facility code, so that's like, what office or campus or whatever you're actually belonging to, and you've got some parity bits in there as well. So this is a 26-bit WeGAN sort of format. So this is one way this is one format that the cards can actually hold their data in. But there's way too many formats, and they're very loosely standardized. So basically every company decides, I don't know, we want to put the parities in a different place, we want to put all the company ID codes and the card number in a different place. So one of the things we've had to deal with in Walrus is dealing with all these different formats, which Dan will probably point out at some point. But yeah, basically the cards, when it comes down to it, the HID and EM cards just hold a secret number, basically. And they're just a fancy way of giving that number to the reader. So let's talk about the way that they actually give that number to the reader. So in the protocol sort of classification, I want to talk about how the cards talk to the reader and vice versa. What do they have to do to each other? How do they have to talk to each other to give the information to actually make this whole thing work? So with a in the first dark ages, no, that's terrible. And when we started, when we would have ID cards, right? The way that you identify is actually, the protocol here basically is you validate the ID card by looking at, its holograms or its secret, stuff they do to make it untamperable, supposedly. Or in the case of keys, for example, actually holding it is the difficulty of actually cloning it. I realise that's a terrible thing to say at this conference. The difficulty of actually being able to get it and clone it is what's sort of the protocol there. And I'm sure you all know what keys are, and keys are for a conference that's based around lockpicking and keys. I'm actually very terrible at drawing keys, so sorry about that. So what about RF access cards? So we have a ability to do something special here, right? We have maths and electronics on our side. What can we do here to sort of improve the situation? Well, not improve the situation, what can we do here? So you'd expect, hopefully, that when we introduce these RF access cards, we sort of, we took the opportunity to sort of improve security a bit here. That's what you'd hope, at least. I mean, we have things like elliptic key. Well, we have encryption in general, right? We have fancy encryption. This is supposedly ECDSA sort of thing. Hopefully, you'd hope that these cards will be using this kind of technology so that, even if you can clone them, you can't clone them, basically. It's like your credit card. You can't clone that unless you get the actual cryptographic secret embedded into the actual chip itself. Unfortunately, at least for HID and prox cards, these cards simply just tell you the number stored on them straight. And as an additional thing, they'll tell you over and over without even being asked. So you provide power to these cards, and they'll spit out their magic number bit stream over and over. And so there is no protocol there, basically. You power up the cards, you get the number, and then, obviously the real reader will be checking that with the controller to see if you're allowed to put into location. For our point of view, it makes it very easy to clone. So when powered, these cards will repeatedly output their stored bit stream. No authentication required. So this is awesome for an attacker. So the card's busy, we do a drive-by, or as you'll see in Dan's part, we do a walk-by. We power up their card, without them knowing. We use Proxmark, which Dan will talk about. It's a sort of tool to interact with these cards. Grab the bit stream and then replay it out to a reader. And it's just like the card being there. There's nothing special. So that's a replay attack. And in the instance of HID prox and EM, since the data, the card is outputting all the data it has, there's no secrets once it's told you its card number and all that, the bit stream. So basically, once we have that, we can clone it 100%. So from the point of view of HID prox EM, having this just makes card cloning easy. Card cloning is exactly the same as reading the card normally. Now, companies aren't dumb. I realise that's probably a controversial statement, but they don't obviously have thought about this somehow. So what was the plan here? What was the intention to actually make these things secure? And Dan told me he has no idea what this is. This is a pipeline. So initially, HID Corporation controlled the production pipeline. That's how it works, right? They just pop the cards out of the pipe when they fall when you get them. So they controlled the manufacture, the programming, and the distribution originally. But then slowly, one by one, this sort of fell to the wayside. So originally they controlled. You can't just buy these, like you can now. You had to get them from They'd started a relationship with a vendor, and then they'd sell those to security companies, and then they'd just use them for specific projects. You couldn't really get them separately. So that fell by the wayside, so you can just buy the cards separately, and then eventually you could buy the program as well, or people, by people I mean China, figured out how to, replicate these cards and program them, which is great. And then eventually they just lost the manufacturing side of things. So people made T5577, which is a chip that can basically emulate HID prox, EM cards. You can program it, and it will take on the RF characteristics of any of those cards and more, and then you put the data you want on it, and then that's what you do. And much to my chagrin of some of my co-workers, who may or may not be sitting in the audience and may or may not have just laughed, I use this to clone my cards at work. And this card this chip is so well used these days. I actually have it like implanted into my hand here. So I can clone, these HID-Prox EM cards with no security onto my implant and then use that to set if my cards will work and stuff like that. So these chips everywhere. So what was HID's sort of reaction to this? Well, their reaction was to add more formats because that's what these guys love doing. So they introduced the corporate 1000 format. And you're probably asking, well, how does this actually solve anything? And you would probably be right. The cards are still going to be spitting out that data, whenever they're asked, to whoever they're asked. The format will be different. The intention was that HID would reserve a certain part of the bit stream and not allow other people to, program their cards with that same, facility code, for example. That only works if HID is the only people. HID Corporation is the only company that can actually, produce these cards in the first place. If anyone else can just produce them and emulate them, that format doesn't provide any more security. To their benefit, they didn't really say that it was the solution to all the problems, but they sort of implied that this would prevent the card cloning problem somehow. I'm not entirely sure what they were getting at with it. So the next kind of card I want to talk about is Andala. So on physical RF level, this is boring, so whatever, frequency, blah, 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 blah. Okay, so data. So they thought, okay, they tried to learn from their previous thing. Maybe having a card that just spits out the data, straight to whoever wants probably is a bad idea. So they introduced something called FlexSecure trademark. So FlexSecure basically takes an existing weekend number and basically it obfuscates or encrypts it. So the first version's just shifted all the bits around on a site-specific format, in a site-specific manner. The newer kinds actually perform some kind of encryption. So the thing, just to step back a little bit, because that makes presentations interesting going backwards and forwards, is the facility code is just a number, right? And the card number is just a number, surprise. So what we can do is, once we've collected a facility code and a card number of a legitimate card, we might try and play it on a door, on a reader, and that might be a valid card, but it doesn't let us into that room because it's a super secret room that Dave doesn't let me in, for example. So what we can do is, we can just change that number, adjust the parities, or in this case not, because I got lucky and we don't have to. So all I've done here is just incremented the card number, gone up one, and then the idea is you play it to the reader and it's happy. So not only, the format is very malleable. Once you see it, once you have a facility code and a card number, it becomes very easy to sort of like move up and down the card number space in that facility, and pretty easy because they don't try to randomize or anything. The software out there will just pick a start point. Often it's just like 1,000 or something like that, and then they'll just increment for each new card that you ask to be programmed. So what Andala did was, what FlexSecure does in Andala is it takes the normal WGAN format, takes a customer-specific key, so like encryption key, a key, and obfuscates or encrypts it. So the point is, and from here we can no longer tell what the original card number is or the facility code. But the trouble is the protocol is still exactly the same, and yes, it's the slide again. So the point is these Andala cards still will output that encrypted or obfuscated bit stream, to whoever's asked, no questions asked. So we can do the same thing, right? We collect the bit stream, for a drive-by, walk-by attack, and we replay it to the reader. So we don't know in this case what the actual bit stream represents. It doesn't matter though, right? This is still just a completely effective replay attack. So there's a tiny bit of extra security there, and I was just doing a bit of research. I couldn't see that the Andala actual encryption obfuscation protocol has been reverse engineered yet. So that's something I'm interested in if it hasn't been already. So Andala, exactly the same idea on the protocol, right? The protocol hasn't changed. You power it up, it spits out the number. Okay? Not great. So yeah, you've seen here in all of these things, the key weakness here has been the protocol, right? When I say protocol, I mean very loosely, right? The reader gives the power, asks for the secret, and the card gives the secret, right? That's not exactly RFC level, anything. So what happened here is, well, not what happened, I don't know, this is the order that plays out in my head. MyFair came along. Yeah, I know, great. MyFair is a thing. Now, this is specifically MyFair Classic. As you'll see, there's a whole lot of variants of MyFair. So MyFair is a card technology based on ISO 14443. Dan has asked me to tell you that ISO stands for International Standardization Organization or something. It's French, so they swap the letters around or whatever. Well, you know how it works. So it's a standard. If you haven't heard of ISO before, probably heard of ISO 9001, whatever it is, the most boring one. So I should be more specific. ISO 14443 type. This is actually MyFair is actually ISO 14443 type A card, because there's also a type B 14443 card. And the reason for this existing is because Micron, the original company, well, there's two companies basically, and they were both trying to compete to get their existing proprietary specification turned into a standard, right? Because standards means that everyone has to, use them and big money and all that sort of thing. So Micron, which eventually sold their rights to Philips, which is NXP, and then apparently Qualcomm wants to take them over, but China's saying no, so we're not entirely sure yet. That's a recent thing. And on Type B, we have Innovatron, which is the most terrible name ever. So these two companies were battling it over, and basically they couldn't decide who should actually be the standard. So it was just, bugger it. Let's make Type A and Type B cards, solve the problem by not solving it. So I know that's the XKCD joke squared waiting to happen, but you've seen it all, so I won't show you that XKCD slide again. So MyFair implements part 1 and part 2 of Type A cards in ISO 14443. So it's got a frequency, so now we've moved up to high frequency. So these cards generally, as Dan probably won't talk about, but he should talk about, is these ones are slightly harder just purely practically to clone because you have to be a bit closer. But that's all that is. And so there's a variety of modulation and encoding formats here used between the reader and card, but it's just the usual. And surprise, they're still weekend as how these cards are powered, right? They're fancy and stuff, but they're still just weekend underneath it all. But with a little twist. So basically, what the difference is that the reader not only has a EM field emitted to power the card, but it also uses that same field to send data to the card. So that's quite interesting. You have to do some silly things to, actually power the card effectively, but still be able to actually have data going to it. You couldn't just use on-off keying, for example. You can't just turn off the field to represent a 0 and turn on the field to represent a 1. And there were some lights going on.
Sorry, we're just doing this.
Test. Okay, well, so, if there was a whole bit stream of zeros, for example, that would be bad because then it would stop sending power and the card would die. So there's some interesting encoding that goes on there to ensure that you can send, any bit stream on that same field, but it will still be there, active, long enough for it to actually send power to the card. It's kind of interesting. So onto the data layer of MyFair, because RF is, even though this is a supposed topic for my talk, it's out of my depth a little bit. So let's talk about the data for MyFair, for example. So with MyFair, it's a little bit more complicated. So you don't just have a single boring 26-bit number, for example. It's sort of like a memory card sort of thing. So MyFair comes, for example, in 1K, 4K, so 1 kilobyte, 4 kilobytes of memory. And these are divided into blocks, and they can also be written. So those are the two sort of main differences in the data area compared to the previous cards. They're a bit more structured, they're larger, obviously, and you can actually write to them. And so this is what a sort of MyFair sort of layout would look like. So you have, each block is 16 bytes, and you have 4 blocks per sector, which is this. So you've got 4 blocks in a sector. And the first block is just manufacturing data and then boring stuff. But then what you actually have, yes, the blocks. But in each block, each sector, you have a key, 2 keys, and some access bits. So this is interesting in that, it's not, you can see that there's a little bit of intelligence here into actually controlling the data on the card. So as you'll see, there's actually keys, for example, in cryptography that come into play. So what will happen is in the context, so MyFair can actually be used, sorry, just jumping all over the place, MyFair can be used not just for access control, right? I don't know what you guys use here in Melbourne, but different transport, stored value card things, for example, are based on MyFair, or stored value things like that. So, the value can be stored on one of these blocks and then secured off by one of these keys. So in the world of access control, the access control data, which is often just the weekend number again, is written onto one of these blocks and then set so that you need a key to actually read that access control data. So the protocol of these cards is based on, that should say, ISO 1444443 Type A. So this is our first taste of real crypto, real crypto, right? You'll see why in a second. So the first use of this real crypto is in mutual authentication. So previously, card was asleep, reader was doing its thing, bring card to reader, card wakes up, weekend effect, cool. Then the reader, previously the reader waits for the card to start spitting out its number, and that's cool. In this case, nothing happens. And yeah, nothing happens. The point is, both the card and the reader must prove knowledge of a shared secret. So this sort of is intended to avoid the problem of the cards just indiscriminately spitting out the data that they hold. So they do this through a cryptographic protocol. I won't go too far into it. The idea is that there's a back and forth exchange. Now we have a bidirectional data stream. That's how we can do this. So you've got nonces, you know what those are, for example, randomly decided things by each of the things, and then they each modify those nonces in a way that proves, they modify those nonces with a shared key to prove that they have this knowledge of the shared key, but not actually share the key itself. So this prevents replay attacks and card cloning, supposedly. Now, if you remember back there, I said, oh God, what did I actually say? Oh yeah, real crypto. So the crypto algorithm here, the actual cryptographic primitive that's actually used for the actual enciphering of the data is called Crypto1. It's a stream cipher. And I can see that I'm running out of time, so I'm not going to tell you what a stream cipher is. But you need to know that it's proprietary. So originally, hardware analysis was done on it to actually try and figure out how the algorithm actually worked. And then traffic analysis was done, which broke the other half of it. So this, in theory, shouldn't matter. In cryptography, it shouldn't matter if your algorithm is completely known back to front. A cryptographic scheme should work. The only thing that needs to be kept secret is the key, or whatever is actually specified to be secret. The algorithm, the public keys, everything else should be able to be public knowledge, and the cryptographic system should work perfectly fine. And that should be the case here, right? So, as you can probably figure out, the answer is no. That Crypto1 algorithm turned out to be weak, and the implementation of it in MyFair actually turned out to be weak as well. So there's two main attacks here. There's one's called the dark side attack, which is either very cool or very not quite so cool name. So this attack works by sending messages to a card. So it fakes a reader. It sends messages to a card to try and authenticate with invalid parity bits. Parity is like an error correction sort of thing. And it uses the fact the card will either respond with an error message or it will do nothing. Now, this can be used to generate what's called an oracle. So an oracle in the cryptographic sense is like an information leak, basically. It's leaking a little bit of information. So by the fact whether the card responded with an error message or not, that'll help us slowly with maths figure out what that key actually is that's being used to protect that card. The other attack that's being used here is what's called a nested attack. So looking back at the original diagram, each block has a key. If you know one of these keys, what the nested attack will do is allow you to find all of the other keys. And this is actually more useful than it sounds, because often at least one of the keys will be some boring default key, right? So like 1, 2, 3, 4, 5, 6 or something like that. So manufacturers or implementors of the actual MyFair technology will often secure their data with a secure key, but all the rest it's blank, so they just leave it with default keys. So this attack allowed us to use one of those keys and then find out the actual key that we don't know. So combining these two attacks is obviously pretty effective, because you use the first one to try and find a key if it's not the default one, and then you use the nested attack to try and find all the other keys. So what NXP did was introduce the MyFair Classic EV1. So the way they responded was by removing that difference in the error handling, so that oracle is now gone. We can no longer try and get little bits of data that will let us figure out what the key is. And they also hardened the cards to nested attack, and they did this with maths. And so the researchers found, well, what they do, of course, researchers research, and they just find another attack called the hardened nested attack, which uses more maths. So MyFair responds by introducing MyFair Plus. So in this situation, they've just said, well, if Crypto1 is bad, and Dan is telling me to hurry up, so I'm going to speed up a little bit here. So what they do is they replace Crypto1 with AES128. That's AES is a well-known standard sort of, you use it all the time on the web. And that uses, the only downside of this is that they insist on giving you a way out. So this is, AES will only be used in security level 3. but you can still downgrade that security, and you get no prizes for guessing that security level 1 on these cards is just crypto 1 again. So you'll find often that people have upgraded their cards because it's more secure, but they haven't changed the readers, and because they haven't changed the readers, they still need to use security level 1, and so absolutely nothing's changed because they spent more money. So then they introduced MyFair Plus EV1. Yeah, EV1. So this also introduces a nice sort of thing called, well, imagine we had a normal card, and it talks to the reader, and that's cool. What would happen if we took that card, basically we do a little sort of like a portal here. So the reader talks to us, and we talk to the card, and then the card talks to us, and then we talk back to the card. So basically, it's like there's key fob attacks, wireless key fob attacks for your car, where you can, be far away from the car, but still interact with their key fob, and you can be interacting with their car, and you send the data across like a big proxy. So this is a replay attack at distance. So what MyFair Plus EV1 introduces, which is quite cool, is what's called distance bounding. So basically, if the reader doesn't get a response back to its challenges in a very short amount of time, it will assume that that's because you're sending it too far, lag, basically. You're trying to send it far away to the card and back again, and it won't allow it. So basically, that's called distance bounding, and that's actually quite a cool sort of physics thing. It's kind of obvious when you think about it. You can actually use the speed of light, which is the speed that this data is being transmitted, to try and restrict the data, how far this data, the challenge can go from the reader before you're actually allowed to, before it times out. And then there's all these other variants, MyFair Ultralight, Desfire, and EV1 and EV2, which I'm not going to talk about, thankfully. Don't worry, Dan. Okay, the last kind of card I'm going to talk about here is called HID iClass. So this uses ISO 15693, boring, frequency, la la la, data. So this has the same sort of idea as well. So 8 bytes, because why not? Blocks, you got some data that's read-only, serial number, confident info, ePurse, which I'll explain. You got some keys, and you got 2 applications. So you've got some static data, and then you've got the rest of the card is made up of arbitrary data, which is split into 2 applications. We classify them as application 1 or application 2, surprise. And there's 2 keys for each of those applications. So when I say application, I don't mean like, Angry Birds or whatever, right? I mean application in the sense of like use. So application as in the implementer, who's actually using it, what are they using it for? So there's one of these applications in the word of iClass is used for the HID application. And this will actually store just the original weekend data again. It's still there. And then the second one is it's supposedly meant to be used for other stored value systems and stuff like that. If you pay enough money to HID Corporation, they'll tell you the keys so that you can start using application 2 for your own use. But I don't think anyone ever does it, so no one cares. So the protocol in this situation is the same sort of thing. There's a challenge response to the situation. You've got your cryptographic algorithm, which takes the nonces and modifies them so that you can prove ownership of a shared secret. You've got ePurse. So the ePurse is a thing that anybody can read, and that's the nonce that the card wants to use. So there's a number that needs to be used in these algorithms called a nonce to prove that you're not just replaying the same response back. The challenge will be the nonce that always changes randomly, and your response will have to include that nonce some way, in a way that proves that you know the key, the shared secret. The interesting thing about this is that the nonce, there is no RNG on this card. iClass cards don't have an RNG. They can't make random numbers themselves. So instead, they rely on the ePurse block. So there's a block that anyone can read. That's the number that you have to use in your challenge to get into access to the card. And then the card actually relies on the reader actually changing that number after it's authenticated. Which is pretty crazy when you think about it. I mean, the same reader could just authenticate with the card, not update the reader, the ePurse, and then it will be able to use the exact same challenge. It will get the exact same challenge, and it will have to give the exact same response for the very next read, which is pretty crazy. And you've got the shared secret, just like in before. So this is the application 1 key. If we're authenticating for a block that belongs to application 1, we'd use application 1 key in the authentication protocol. Now, it seems a bit silly for every card to have a different key for every application, because then every reader will need to know every single key to get to every single application on every single card. So instead what we do is we call something called key diversification, where we take a single key that belongs to a site, like a campus, whatever, take the serial number of the card, input those to an algorithm, and that spits out a new key. So basically, key diversification takes an existing key and some other data and makes more keys from it. So I've got a site-specific key, we take the serial number, and that produces our application keys. Now, this question mark is meant to represent something which I'm supposed to remember. Oh yeah, you'd hope that they would implement this securely. Like, you've done all this work, so you've done all this work to move from application-specific keys to site-specific keys, so let's make use of that. So, no, basically what they did was the Heart of Darkness attack, very dark, matches the theme feel in here so far. What someone did, and I'm very sorry, I can't remember his name right now, he took an existing iClass long-range reader, dumped the firmware off it, and in there was the key. When I say the key, it's because HID Corporation in their infinite wisdom has decided to just use a single static key for all iClass things. So they've done all this work, algorithms, the key diversification, and then it's just like, well, instead of allowing people the opportunity to make their own keys, let's just use this one. Because it's random, and so it's great. So, and if you don't believe me that's key, you might know this person and some of those other people, and yeah, it's on Twitter. So what iClass did was realize that that's probably a dumb idea, so they started allowing people to use site-specific keys. But there was another flaw in the actual key diversification algorithm, which made it even more vulnerable. So even though you had a diversified site-specific key, due to the flaws introduced in the way that that input gets put into the key diversification algorithm, it was actually weaker than it was in the first place. So they introduced iClass SE, and it's the same thing, right? They introduced AES-128, they realized this was a bad idea, let's just use well-known tested protocols and crypto schemes, basically. So that was a very rushed-through example, walkthrough of some of the technologies that Dan was going to be talking about. Sorry, Dan, you've got 20 minutes. But general trends include, so you can see general trends here, they move from proprietary security by obscurity to well-known open standards. That's a good thing. They love reusing existing brands even across large jumps in security. That's a very confusing thing for me. But you saw in the end there, I sort of said, MyFair did all this thing, and eventually we added enough names to the end of the word, and we fixed enough things, and so it seems okay now. And then, iClass did the same thing as well. So everything should be okay now, right? There's a secure, implementation of each of these cards out there now, right? The answer is no, everything's still not right, because upgrade costs, right? You have to actually obviously upgrade not only your cards but your readers in most of these situations. So companies just obviously don't want to spend the money to do that. And ignorance, and I don't mean malicious ignorance, I mean they just don't know. No one's told them, and they were not going to find out themselves that their card systems are still vulnerable to cloning or weak keys or whatever. Or they'll just straight up think it won't happen to us. The classic pen testing excuse, or we can sign away on the risk on that issue because it won't happen to us. So there's still definitely viable attacks. And what Dan is about to talk about now is using some of those attacks and the application that we've developed to actually make using those attacks a lot simpler in the field. Cool. Awkward.
Cool. Hey everyone, sorry I don't have 200 slides, so this won't take so long. Cool, is that working? All right, cool. Yeah, so thanks Matt, that was awesome. So yeah, like Matt said, there are still ways to attack RFID card systems. There's still those that are viable to actually being cloned. And why does any of this actually matter to us, right? So Matt and I do a lot of red team engagements. Since last year, they've pretty much doubled in the amount we've done. And part of the goals on these jobs is to bypass the access control system and gain persistent access after hours or something to the client's building, or get server room selfies, which is quite like a highly prized thing at our organization. So I'm going to talk a little bit about some of the card cloning devices. So to run through them really quickly, Proxmark 3, this is the industry standard card cloning device that Matt was talking about. It does low frequency and high frequency, so you can see there it does the hit prox and high tag EM400 T55X and all the rest of it. There's quite a diverse tool to have in your arsenal. If you could pick any of the card cloning devices, it is pretty expensive, but there are knockoff versions, so you can see, I hope I don't turn this off. You can see that one there. So this is the original Proxmark. This is a knockoff one that I bought for about 100 New Zealand dollars, including delivery. So compared to 300 USD, it's a lot better. Chameleon Mini, so this is another device created by Casper Oswald, and this does the high-frequency card. So you can actually read the sectors and the encrypted sectors and dump that. Like, if you can dump that card information, you can then emulate that within this card. So the big difference here is this card isn't so much to do replay attacks, but it's actually just to emulate the card on the device itself. So you can have up to 8 cards emulated in this device at once. And then there's this device here. This is originally this was made by Head Corporation. It was made for car parking sort of spaces like Matt mentioned, where you want long-range card reads. Now this doesn't work on passive. This still works on the this doesn't work on active-based tags. It still uses the normal head prox cards, and those are passive. So this reader will actually power that card. With our experience, we've seen this about a 0.5 meter range. So what we do is we have one of these devices, and it's been modified by Bishop Fox originally. And what they did was they added a board basically to take the weekend that comes out of the reader, write that to an SD card, and then you can clone those cards later using another device. So as you can see, there's a bunch of different card cloning technologies, but what's really, I guess, the problem is that there is a bunch of difficulties. So things like there's no common tool that you can use to control all of these devices. Most of them are the CLI-based sort of operation. There's also no common database to store your cloned cards. Cloning cards surreptitiously can be pretty tricky. To use the Proxmark, for instance, you would plug it in via USB to your computer, and then you would need to pick that up and sort of like scurry along the person and try not to look suspicious, and that's pretty difficult with a laptop, a card cloning thing, an antenna, and all this gear, right? You look pretty obvious. So yeah, the existing Proxmark does have a standalone mode, but we found that's pretty sketchy, and what I mean is this is unreliable. The feedback is quite, like, you're not sure if you cloned the card, and when you're doing a red team engagement, you kind of, most of the time you have one shot at this. You're going to try clone that card, and you want to know that you actually got it. You don't want to walk away and be like, oh yes, I got the card, and then toop, nothing. It's like, oh great. So yeah, you really want to make sure you actually have the card. And then, yeah, like I mentioned, a lot of these devices, they're CLI based, and sure, for us that's fine, that's easy, but we want to make this quite like we want to make card cloning usable and let, like, layman's people be able to clone cards, and it should be a good fun experience. It shouldn't be something that you're struggling to do and trying to make sure that the antenna's connected and oh my god, like it's just, yeah, you want it to be a nice fun experience. So we got to planning and wireframing out what we kind of wanted the app to look like. So that was kind of the main wallet screen that we wanted to have. You click on one of those and it goes to the card itself. And then you have like a little add button here that you can press and add new cards, and you can connect, basically you connect to the different types of card cloning devices in different manners. So the most common one is with the Proxmark is to use USB to serial, and the same with the Chameleon Mini. And with the Bishop Fox, I'll talk about that later. So here was the basic. So this was just when I was trying to get a bit of a POC going here, because I thought it was a good idea, but good ideas are nothing without implementation. So I put together a small Android library, or an Android application, and I was basically just using a pre-built library to talk to serial devices. And this was kind of a glorified terminal app. Basically, you plug in your card cloning device, and then you type it in a command here, and then you got the response. But it worked, so that was great. I was like really stoked. I showed Matt this, and this was roughly the time that he got his his implant in his hand. So he wanted to use this to, program his hand kind of on the fly and, in a lot nicer way. So now Matt, this was the point essentially where Matt came along in the project, and you can tell Matt's quite intelligent. He's a beast at coding and stuff like that. He's really good. So the app soon went from this horrible thing to this quite nice looking app. So what we tried to mimic here was Google Wallet or Apple Pay. I'm not sure if they've changed the names of them now or what's going on there, but essentially we wanted a place where you can store your cards and write them to a new blank card if you need to do that. So I'm going to walk through the process real quick of what card cloning looks like using the Proxmark 3 and Walrus. So this is the app we made. Just bear with me as I run through these. So Proxmark on the right is connected to your cell phone, and you would go add new card, and then at this point you give the card a name. So here's just hit Prox test, and then you would hit the read card button. So once you've done that, it asks you to choose a device. So you would select the device that's plugged in. In this case, it was a Proxmark. And then it goes into the screen here where it's waiting for a read. So at this point, you're kind of like armed, and you need to essentially walk past your target and clone their card. Once that happens, so you introduce the card into the antenna, you get a read, and that stores the card into your database. So at this point, it grabs the location, so that's helpful to know where you actually cloned the card from, and will be useful in future features that we're adding. So at this stage, yeah, you can make some notes about your card, where you got it. It grabs the date and the number itself, so that's the important bit, and then it auto detects what type of card it was. So you save that into your database, and now essentially you have a clone version of your target's card. So this is great to get it to this stage, and this is actually working. These are screenshots from real cards. Don't copy them, please. Okay, so at this point now you can tap that card and you can actually use it. And what would you want to do? Yeah, you'd want to pretty much write it or emulate it on another device. So again, you would introduce a device such as the Proxmark, and you bring up a new blank card. You hit write card, and you now have a clone of your. You have your own access card essentially to get into the building. This is the point where you walk in, you put it around a lanyard, and you're in, and you're a trusted employee because you've got a lanyard that lets you into the building. So that's kind of the card cloning process. It works exactly the same with a Chameleon Mini. And we had a little bit of fun with this. So what we were trying to achieve essentially was, so you know what ward driving is? Is that the one with the Wi-Fi? Yeah. So we called it Walrus driving. Essentially, it's like a bulk read mode. So you can put the device into bulk read, and it'll just keep on reading. So you can tap a card, tap a card, tap a card, and it'll just keep on pulling all of them in. So obviously, if you tap the same card twice, we've built in a little thing there to recognize that, and so it won't just fill up the database with 100 of the same entries. So this is kind of this is where if you weren't sure when you're actually going to get the card, you put it into war driving mode, and then you clone as many as you can. So this is an example of what that looks like. So we've got two Proxmark devices hooked up here, and you can see there we've read the same card. So we have to alternate them because of what I just mentioned. Yeah, so that was really interesting. So we were like, great, we can get multiple devices working at the same time. And then we were like, but yeah, how many? So we started adding more devices, and we started trying to test if we can add different types of devices. So there's 1, 2, 3 Proxmarks and a Chameleon Mini, and as you can see, you're getting the reads down there. Okay, but what about the Tastic RFID thief, right? Because essentially this allows you to clone cards at a longer range. And then once you have that card, you can use the Proxmark to essentially write that. So I'll show you a video in a little while, but what we did is we modified the Tastic RFID thief again to add Bluetooth to it. So if you can have a look at that there, the little HC06 module, which is about $4 on eBay, we chucked that into our model, and yeah, essentially gave it Bluetooth. So we can now connect to that via Bluetooth on your phone, and once the device is paired with a long-range card reader, you can just receive cards. So a couple of disclaimers: the UI is a little bit out of date. Only clone cards, if you've been permissioned to do it. This was a video we did to show how it works, so we obviously have permission. Okay, so this video is, I'm going to walk through it and try not to be too annoying, but this is the intended use, or our advertising video, right? So this is how the card cloning process will work for us. As the attacker, you start setting up, like this is in your office, you start setting up your attack device. So what we do here is power up the long-range card reader, and you can see the Bluetooth module down the bottom there. Now this was kind of early stages, so a lot has changed, but you essentially the Arduino didn't have enough power, so we had to provide external power with that USB hub there. So this is your long-range card reader now kind of ready to go. You pair it with your with the app. So that's the app there. You can see the device has been paired. And now you give it a name, and then you would put it into bulk read mode. So like I said, that was like the mode where we were like armed and ready to go and collect cards. So I've given it a name here. We put the card reader inside of a bag, and this is kind of what we really do. We walk around with this bag and hope that it doesn't give us cancer while we're cloning people's cards. So this is the target building here. It's one of our sales guys. So he's leaving for the day. This would be your mark or your target, right? And I'll show you a little bit of a thing, this pause frame here. So you see, you can see he's wearing his card in an easy to sort of see place. A lot of times people would either hang them around their neck or somewhere there, but as long as we can see them, we know what we're targeting. So don't know if you saw, that was the card cloning process. So literally walk past him, managed to get a read, and now we have that person's card. So what the next stage is you would do is you would plug in another device. So what I do here is I pull out a Proxmark that I have. I attach that and write a new blank card with the new card that I just got from our target. So now essentially I have access to the building, and that's kind of just how easy it's, we want it to be this easy, and that's how easy it's become. So if you're ever using HID or something like that, it's a bad idea, because yeah, we'll do this, and it doesn't take long, I promise you. Cool, so yeah, future plans, we want to add some features like brute force modes based on like location. So, where you capture that card, try brute force cards based on how close they are in proximity to that area. Sharing cards between multiple phones. So if you have two consultants on a job, one's maybe armed with a long-range card reader, he can clone the victim's card at a coffee shop down the road just by standing next to them in the queue or something, and then he should be able to share that to me or whoever else is waiting to get access into the building. So they share the card, and then you write the card using a Proxmark, and you're in, right? So. Gamification. This is I'm not too sure. Matt's not really fond of this. You can see him. So gamification. I want to kind of make this like fun for us during these red team engagements. So I've taken out the screenshot, but essentially there's a well-known game where you're capturing you're capturing different things. I think it's like Pokemon something, Pokemon Go, where you're capturing eggs or whatever you capture. I don't know what you're doing there. I don't play it, sorry. Well, for us, our eggs are the cards, right? So yeah, we want to make it so you essentially have like a location-based screen that shows you where you are, and then where the cards that you've cloned are based, in a map view, so you can, just walk up to the building and replay your card. And then, adding additional device support. So this might change. It depends kind of like how much the technology is used. MagSpoof is for cloning magnetic stripe cards. BLE key and a bunch of these other devices are kind of not really in the line of card cloning per se. They kind of injected, it's something that you can inject behind the reader. So those new fancy encryption techniques and mutual authentication that Matt was talking about that's been introduced into newer cards. What you can do is bypass those with some of these newer devices where you essentially, after the card and the card reader has done its fancy mutual authentication, it just spits out the number over the back end. And so some of these devices are like a hardware tap that you install behind the reader, and then just get that number and send it by Bluetooth. So. Workshop. So yeah, we're going to be running a workshop at 1:15 if you want to do some card cloning. Basically, what this is going to be is like a massive debugging session for us and test how our app handles on different people's phones. And yeah, we're not stealing your cards. But yeah, that's it. So the website for if you want to download the app, you can find it on the Play Store. If you need help on getting started, or there's some documentation and all that on our website. And then the project is open source at GPL 3, and it's on GitHub. So if you want to clone it, make commits, change it, do whatever you want. Open issues, just report things, play around with it, tell us how it works and what sucks and what doesn't. That'll be really useful. So, cool. Thanks very much. Questions?
I don't think we have time.
Do we have time?
No.
You can have a minute.
Okay. Sure.
Questions?
2 questions.
Do you support loading reads into emulation slots on the Chameleon before just writing the blank cards?
So they actually write to the emulation, like the card slot on the device itself. Yeah. So they write to the emulation slot. Yeah.
When there are multiple cards in the same range, can it clone like all at once or work at all?
Yeah, so it kind of depends on the technology. There's like collision detection and a whole bunch of like things where especially if you walk up to like a reader with your wallet and you try to put it up on the reader and you have like 5 different cards in there, it's most of the time it's going to be like, I'm not sure which one. There's multiple cards or whatever. So it's a little bit tricky. I guess it just depends. Like, if it gets a chance just to read that card, then yeah, it's going to get that card read. But it's a little bit of things I guess we need to test and play around with to see how it reacts with that. Any other questions? Cool. Awesome. Thanks very much, guys.